Okay, welcome to applications. We're looking at some applications for the solving using the idea of differentials and solving the idea of integration. So this is a bit of a funny place to put it, but it's got to be explored at some point. So you'll be definitely doing these in Mathematics 1. Initial value problems involve equations that have in their content a differential. So instead of saying y equals some function, it says a differential equals some function. So it's like we've done the differential and we're just highlighting that it is in fact a differentiated equation. Now how do we undo the differentiation? We integrate. So we're going to do this method here using some integrations. So these initial value problems are something that will be discovered during your time in Maths 1. And so it's very important that you're able to do those. Okay. And so we'll have a look at this today. Okay. What does it mean? Now, differential equations have as their solution DEs. So this is kind of very important. Y has a solution, a normal equation has X as its solution. Has X as its solution. That is the x-intercept. When you do a solution for a normal equation, you find the x-intercept where it cuts the x-axis. Okay, this is a new class of equations. Okay, a DE doesn't have an x-intercept as its solution. Stay focused. Except that is the x-intercept. DEs have a whole function. So what's the DE function? So we're used to finding a number x which represented the x-intercept. These guys have a whole function. Okay, so there's some function that represents the solution. So that's a very important distinction. To solve a differential equation is to find some function that has the differential. Okay. So that means we're going to integrate. So if we integrate dy dx as an undo operation, that means that we should end up integrating d dx. What you do to one side, you do the other. And so we're going to integrate 5x minus 1. So this means that we get y equals. This is undo. Okay, undo. So y is equal to, and we integrate the right hand side, to find out what this function is. What is this y function? Okay, so we go up and under 5x squared divided by 2, and the constant becomes conjuring, so we get an x, okay, plus c. So this is our constant solution. Okay. Now we have some initial conditions, and the initial conditions are that the curve passes through 1, 3. Okay. So when we put x equals 1 in there, we'll get this. So we did this when we found the y-intercepts, didn't we? xy (1, 3) in y equals. So 3 will be equal to 5, 1 squared minus 1 plus c. So in this case here, 5 on 2 minus 1. So we can make that 2 on 2. We can 1 squared is 1, so 5 on 2. So I need to put it all over. So we're going to minus 5 on 2 and plus 1. So therefore, C is equal to 3 plus 1 minus 5 on 2, which is 4 plus, well, minus 5 on 2. Sorry, I'll get rid of that. Minus 5 on 2. We'll use our 1 in disguise. So we end up with 8 minus 5 on 2. 8 minus 5 is 3. So C is equal to 3 on 2. Therefore, y, the solution, is 5x squared on 2 minus x plus 3 on 2. So for that particular equation, we've now got a solution. So this one here is called a general solution to our problem, a general solution. And after we've worked out that we want to try out what happens at a particular point in time or distance or whatever it is, then we rearrange and solve for constant. And in this case, we've got 3 on 2. And so this represents a particular solution. I know it's language, but nevertheless, a particular solution. Or was integrated. Okay? So we integrated it, solved for C, using some pre-information, and we were able to do that. When we find the values of C, we can see that this is a family of curves. Okay? We can see that that's a family of curves. And so a family of curves represents the solutions. Because once we know we differentiate them, the constants are going to disappear. But we've learned that also. Alright, so we've got another solve the differential equation. It's expressed instead of being dx dt. These are called initial conditions. So this is an IVP, initial value problem. Okay, and these are our initial conditions. Now, it's very interesting to recognize that the solution of an equation is in fact a function. Okay, so what's the function so what we have to do is integrate. Okay, so f of x, in integrating both sides, okay, what we're going to find is the function, and because we generate a c, we generate a family, so x 4 over 4 up and under minus 4x squared over 2 plus c. So our general solution, this is our general solution, contains the c, and so for any value of c, this is a solution for this particular differential equation. Now the function value of our differential equation at x equals 0 is 2. So 2 is equal to 0, 4, 1, 4, minus, now that was 2, 2 times 0 squared plus c. And we can clearly see they're not there. So therefore, c is equal to 2. So our solution, our particular solution, based on the initial value problems, is f of x is equal to x4 on 4 minus 2x squared plus 2. That's the solution function for. If we differentiate that now, we'll get our original. Okay, so that's all that's happening. Alright, I'll change the pen colour back just to give us some consistency. And so what we have is some initial conditions, y and x. X is 0, y is 0, or another way that can be interpreted is that the f of value at 0 is equal to 0. So the function value at 0 is equal to 0, or y at 0 is equal to 0, even though it says it passes through the point. So this changes a little bit in context when you get to do these proper, but these are just fairly straightforward examples. Alright, so we're going to integrate both sides, aren't we? So y will become the integral of 5 e to the 3x. dx, which we know is, well, a chain rule. Be prepared to do a chain rule. I think it's important that you do. Let the u substitution, let u equal 3x. The integration, so stay in the column. Du dx will be equal to 3. So 1/3 du will be equal to dx. Are you up there? Yep. Well, you just got subbed out. So 1/3 the integral, and we're going to put the 5 on top, out the front. E to the u. So the integral of e to the u is e to the u. 5 on 3 was staying there as a constant. E to the u, 3x plus c. Now we've got our initial conditions. So we've got y is 0 when x is 0, and we need to be careful because the meaning of x equals 0 here will mean that this is e to the naught. Okay, so therefore, e to the naught is 1, so that's just c is minus 5 on 3. So our general solution was here, a big family of curves. Okay, our particular solution based on these initial conditions is simply y equals 5 on 3 e to 3x, and c was minus 5 on 3. So that's our particular solution, given the initial value problems that we were set up for. Okay, so if you differentiate this, you'll get this original thing back. And yeah, so it's fairly straightforward, but I'll leave you to do that check. All right, let's have a look at a couple more examples. We've got initial conditions of x and y. So they're our IVP values. Okay, when x is 5, y is 1. So we're going to integrate both sides here. And we'll get y equals the integral 1 over x minus 4 dx, which is the derivative of the denominator is 1, it's on the top, so we can simply implement a solution. So it'll be 2 ln x minus 4 x minus 4 plus c. So that represents our general solution. Let's put the y in over there. So then we need to generate our particular solution. So when x is 5, y is minus 1 equals 2 the ln of 5 minus 4 plus c. So we're using our initial value problem, and so we get 2 the ln of 5 minus 4. So the ln of 1 is 0. So 2 times the ln of 1 is 0. We've seen that before where it crosses the axis. So this whole term here is 0. So therefore c is equal to minus 1. And our particular solution y is equal to 2 ln of x minus 4 minus 1. So that is our particular solution, having solved C. Okay, very interesting. All right, let's have a think about this one here. We're going to be integrating both sides. So y will be the integral of sine squared x cos x so we'll use the u substitution of sine x staying in the column the differential of sine is cos. Now rearranging, multiplying by d, du will be equal to cos x dx. Are you there? Yep. Are you there? Yep. Gone. Replaced by du. Wow. So the integral of u squared. So we get u 3 divided by 3 plus c, which is equal to I'm going to put this up here. Y is equal to 1/3 sine cubed x plus c. Now using our IVP values, y is 1, x is pi on 2, we've had to wait a while, but we now have exact values trig. Sine pi on 2 is here. Sine is that length there, which is 1. So 1 cubed is 1. So c is equal to 1 minus 1/3, which is equal to 2/3. So our particular solution is 1/3 sine cubed x plus 2. So that's our particular solution. That's our particular solution. That was our general solution. Alright, so that was fairly straightforward in the end, and you will encounter those in Maths 1. So a little bit of training here for us. Okay, that's enough for applications. Bye for now.